Second speaker today is David Kelf from Breker Verification Systems, where Dave is CMO, which I think is Chief Marketing Officer. The topic of his talk is leveraging a synthesizable verification OS for bug-free SoCs. Dave is a well-known EDA industry participant, having run Cadence Verification Marketing, driven Synopsys Verification Strategy, and run marketing for co-design, System Verilog, Novas, Verdi, and others. He is now working with Breker on their PSS-based SoC verification products. He has a solid engineering background, has performed many ASIC designs, and holds a microelectronics MSc from Brunel University. It sounds like a Brunel University alumni today. So he's based in California, and I think he had the 4 o'clock start. I'm not sure Nick did, but Dave certainly had the 4 o'clock start. So over to you, David.
Yeah, morning, Mike. I did indeed have a 4 o'clock start. Yeah, so I'm waking up now.
So we can see your screen. Go ahead, Dave.
Okay, so morning, everyone. What we'd like to talk about is some new technology and new concepts called the Synthesizable Verification OS, which Breker has been working on for a while with a number of companies to facilitate and improve SoC verification, of course. You know, a little word about SoC verification. I think we would all generally agree with this at a high level. You know, in the past, traditional SoC verification has been focused on just making sure that SoC blocks are fully interconnected and working properly, and the functional verification of a system has been targeted towards the block level and making sure the individual blocks are functioning correctly. And I think this is almost a hangover from the days 20, 25 years ago, where you had a processor and a number of chips on a board, and the chips will do the functionality, and then you get the whole thing working afterwards. So verification would consist of booting Linux, running real data, and just making sure the SoC was basically functioning. And as Nick, I think, alluded to as well, clearly this is not enough these days, where SoC functionality is spread across multiple blocks and software, and the whole thing needs to be functionally verified correctly together. The infrastructure complexity is extreme. So coherency was mentioned before. Items such as security and other areas need to be made, ensure that they work correctly. Concurrent operations are critical across the SoC, and this leads to bottlenecks and some very tricky corner cases that need verification. And of course, just the sheer size of these things and the complexity requires a much more focused effort. So just running real data and booting Linux on a processor doesn't suffice anymore. We need to go to a much more in-depth functional analysis of these devices. So when it all boils down, what 3 or 4 major areas do we need to focus on to improve SoC verification? Well, the first thing we would look at is what we term a single source of truth. That is creating a high-level representative form of the test content from a specification level, and then generating all the different tests from this, the stimulus, the checks, and coverage models as well. Coverage, of course, takes on a different meaning at the SoC level. We have our very typical sort of coverage models, but we also need to be thinking about concurrency coverage, we'll talk about in a sec. And from an efficiency point of view, shift left now is becoming a much more important focus, making sure we can do things in parallel. So what is this synthesizable verification OS that we believe can be used to solve a number of these different problems? Well, what we've found is that we need some enabling technology to allow companies and teams to write tests at a higher level in a multiple array of different languages, depending on their preference and where they're coming from. And to basically provide, much like Linux provides for a software engineer, a number of critical services to schedule tests and to execute verification operations in a very seamless fashion, and to hide a lot of that from the end users, so the end users can focus on the actual test content and getting that correct. So we've proposed a system here which has three major components. Firstly, providing a series of virtualized operating system services, as we'll see in a second. Secondly, scheduling tests very efficiently. And third, basically controlling the execution of these verification environments. And this needs to be run from a number of different languages, including portable stimulus, as mentioned before, good old C++, which many people are still using, and we need to be allowed for UVM and other things as well. What are the virtualized verification services we require? Well, the idea here is that if we're using a language such as portable stimulus or C++, we need to be able to provide a number of different mechanisms that are common regardless of which part of the verification process you're looking at. So maybe you might be, the SoC level and UVM. You need to be able to perform such things as memory allocation, as Nick just mentioned, have a common register maps, common transaction forms, and so on, and make sure these are portable across all these different phases of the verification operation. There's some examples of these, and this slide taken straight out of the Portable Stimulus 2.0 tutorial that's going to be delivered next week in DVCon. But memory allocation, critical for modern SoC verification. And from the portable stimulus point of view, what we can do is set up a claim on memory and then initialize that with different regions, different size, and then during the test focus, actually execute tests and allocate certain levels of memory depending on what the system is trying to do. So you can see here in portable stimulus, you can basically set this up. In the past, if you were writing an SoC test, you might have to actually do this manually as if you're controlling a bare metal processor. What we can do today is provide the mechanism underneath, much like a Linux OS would do, where we can schedule the memory for you and control that to stress test the whole cache system and memory system very, very fully. Portable registers is another thing that's key. So we could do things like take an IP exact register definition, which is a pretty common mechanism these days for a lot of companies, and generate portable register definitions in C++ in this case. And these would actually follow the classic round model from UVM, but be able to be executed at a much higher level and spread across the SoC and even into post-silicon with a common register map that can be actually leveraged. Same thing for transactions, where we need to not only be able to drive a processor with software in these tests, but we need to drive the I/O, and we can use TLM type mechanisms, again using common standards, and actually drive this through the OS, and the end user does not have to worry about trying to, at the bare metal level, setting up transactions and ensuring that they're all executed correctly. This is all done automatically. So essentially, what we are able to do is provide a model of verification intent in whatever language the end users are working with, portable stimulus, C++, even Python, and then synthesize these verification OSs services into this test content such that it could be used on a simulation emulation platform in an SoC environment. It could be used post-silicon and with UVM simulation. And indeed, if we are working with a final device and you're actually booted Linux on it, the same services can run with Linux, but actually make use of the services that are available rather than actually synthesizing new services into the system. So this essentially allows for a completely portable verification intent to be mapped onto whichever system you're using. And this is really the hidden piece inside using portable stimulus, for example. So portable stimulus on its own does not actually provide a strong level of portability. It gives you ability to do test content, but you need to manually map this across these different systems. Portable Stimulus 2.0 has some new standard mechanisms built in to alleviate this, but we need the mechanism underneath, and that's what the Verification OS would provide us. Test and resource scheduling is also another critical example of this. So if we look at a little SoC here, in this case, a little image processing system, at a high level, you may want to run one specific test where you might take some data from an SD card, run it through a photo processor, and put it out on a display controller of some sort. And then underneath these different modules, you would, of course, have a whole series of different tests, initialization functions, and so on to sort of get this thing up and running. So, this is a pretty common kind of thing you might want to do on an SoC. And we can think about this from a serial point of view and build up individual tests over and over again, and that's great. However, on an SoC, what we probably want to do is have a whole range of tests, which you could describe using kind of a graph format, which maps onto portable stimulus or C++. And what you'd like to do is maybe execute the same test we just described from the SD card controller to a photo processor. And here we can do the whole thing in one thread, for example, and essentially list these tests out in the thread and serially operate them as I'm showing here. And we can maybe do the same thing with a second test where we take data from a camera, run it for the same processor and out on the SD card controller. And this is interesting, and it's the sort of thing that we might actually be creating test content for today. However, it's not realistic at all on a modern SoC to be looking at it just from this serial point of view. What we actually need to do is be able to run multiple tests concurrently together. And this is a key component of ensuring we have a good test system which provides a high level of concurrent coverage. So we may take our first test and put that across threads such as this. So you have 3 threads, maybe on 3 or 4 processors, and we spread the tests across those. And the second one might happen concurrently with that first one, but using resources in a serial fashion, of course, because we've only got a finite level of resources. And we can continue with this and build up all these different tests in a concurrent fashion. And of course, these tests do use resources, and as I mentioned, they are finite, memory being the obvious one. So we also have to allow for scheduling memory. So we might take our first memory region, which has been allocated through VerificationOS, and basically use that to control the data as these different tests are operating. And the same for the second one, and so on. So what we're doing now is building up test content for an SoC here, where the tests are being scheduled in parallel, all automatically, all via an operating system, much again like Linux would do. And so this gives you a very realistic test and really allows you to target this full concurrent coverage of the system, which in turn allows you to very effectively drive a full thorough test of the SoC. The third aspect of this is execution management, and again, something useful at the UVM level, where you might be controlling parallel threads, but essential at the SoC level, where now we might be working with software tests running on a processor, combined with transactions running in a VIP, and we need to synchronize between them. We also need to be driving coverage data, debug data, and so on. So execution management becomes very critical. So for example, on an SoC, I think I'm running out of time, so I'm going to accelerate a little bit. On an SoC, we may take the Synthesizable Verification OS driving C tests and transactions, and then run these on an execution engine which uses backdoor memory access to provide the kind of scheduling that we've just been talking about. You could do the same thing at the UVM level, as Nick mentioned, subsystem testing, where you remove the processor and put a VIP in there instead, which may be driving AXI bus traffic, is the same thing. And here we can use the same tests, the same OS, to drive UVM tests onto the system. And we can do the same thing through post-silicon diagnostics. So this leads us to be able to, excuse me, to drive our 3 pillars of SoC verification much more effectively. The first thing we do is raise the abstraction, encapsulate the single source of truth. So we can drive the thing from a certain high-level specification. We can provide 3D coverage, as you mentioned before, using concurrency, and we can really accelerate this idea of shift left, making sure that we can develop software tests as well as hardware tests and full test content all in parallel. Using this idea of synthesis, as Nick mentioned as well, with the verification operating system services synthesized into the tests, we can very efficiently drive this idea of single source of truth. And this actually does lead, touching on a little bit of what Nick was saying, to the ability to use system VIP and system level test content, encapsulate it and configure it for different systems, and run that both at the UVM level and at the SoC level on the various systems. Pre-D coverage, we mentioned before, this idea of scheduling a number of different tests. You could have combinatorial coverage, which we all recognized, ensuring cover points are met on specific tests. Sequential coverage, which covers a series of tests operated together, making sure that these different sequences are happening correctly and they're fully covered. But most importantly, on an SoC, making sure we have concurrent coverage, that we can check operations together and their resources and make sure we stress test the whole overall system, looking for bottlenecks and tricky corner cases. And finally, we had this idea of shift left acceleration, where by using this VerificationOS layer, we're able to take the same models and map them onto these different phases of the verification process, and essentially perform a lot of system modeling up front, even using a virtual platform environment, then driving whatever block test needs to be performed and using the same content all the way through. So the content is produced up front. And we have various hardware software verification flows. This is an actual customer flow, which was switched from a serial flow with months of delay in there from the verification software guys back to the hardware, and can be turned on its head and executed in parallel. We can accelerate simulation. I'm sorry I'm going very quickly here, but we'll be happy to answer questions and talk in more detail about this if people are interested. Final thing I would mention is this has been used on real environments, and we've seen kind of like a 5x or so improvement in SoC verification making use of this VerificationOS to just eliminate a lot of the donkey work that goes on and put different tests in parallel. Okay, so this is this first time we've actually talked about this concept in public. There is going to be a tutorial executed at the DVCon US next week, and we'll also be putting a lot more information about this on the website and in other different formats as well. So I know this is a very rushed presentation, but if anyone is interested in learning more about this, of course, we'd be happy to discuss it with anyone. Thank you, Mike. Sarah?
Thanks, Dave. Yeah, that was a bit rushed, but you kept on time, so thank you very much. And you say people can come and get more information from you and DVCon next week as well. And thanks for revealing this to DVClub ahead of DVCon. So thank you very much. One very, very quick question, if you can. Is the scheduling done at runtime or test elaboration time? That's on slide 11.
Yeah, great question. So in general, it's done at test elaboration time, but there is some dynamic aspects to it that also need to be executed at runtime. So that's why the execution part of the OS is so important, because it can change and alter the test content and how it's executed depending on resources that become available or go away and things like that. But as much as possible is done up front, which makes it facilitates it for the use with emulation, of course, as well as simulation, if you can do a lot of the upfront test formatting.
Brilliant. Okay. Thanks, Ed. That's all we got time for. So again, thank you very much.